Great. All right. So last time, yeah, we were just getting across basically one of the very first deterministic policy gradient methods. So we followed this story, basically starting from deep QLearning. Deep QLearning doesn't work for continuous actions. And there's basically part of this problem from the last slide where basically the algorithm still needs to figure out how to do this max overall actions. Now it's in a continuous space. And what is going to be used is basically some model is going to be the thing that is the current approximation of this max overall actions. In this case, is this mu model. So how this changes a little bit compared to like prior methods and stuff for DQN is there's still a process for sampling a batch, so we can still make everything IID. And then here now using the target networks, then use those as the thing to approximate basically the max overall actions, because the algorithm needs target values to actually be able to train towards. And then the policy can now be updated by computing a gradient essentially through the Q function, because now you're just kind of like composing these two models together. And this is still pretty normal here for computing the target values and training for them. And the last part that I was saying was a bit different, and we didn't have much time to discuss it, where there are target networks, but they're not updated the same way that DQN normally updates them, where DQN just every 10,000 steps copies the online Q network to the target network. This uses Polyac averaging that copies over some small portion of the online Q network model over to this target model. And empirically, this seems to work okay. But to be honest, this is one of the odder parts of this algorithm that if you look at it maybe a little bit too hard, and you remember some of our discussion about making sure the Q function is a good contraction, this one might start to make you question whether or not this algorithm is an actual contraction. There's just like not really many guarantees that this works out properly. Just empirically seems to be okay so far. Okay. Any questions about the algorithm? Oh, good. Okay. So this is a bit more of the details here on that, because in DQN, this was a nice process, at least a slightly more structured process for being able to copy over the online Q network parameters to the offline. So Polyac averaging basically does this process where it's kind of like borrowing a little bit of the data from some point and then contributing it over towards this other like target. So if the set of parameters here is some fixed set of parameters, using Polyac averaging will eventually result in the process converging to that actual target. Okay, but then, so why won't this work well then when we're doing deep QLearning? Give a little hint. It has something to do with this target. Any thoughts about how this can certainly get off track? No? This, let's say in this particular process here for Polyac averaging, this point is still supposed to be stationary. Is that true for deep QLearning? No. Yeah, it's like very unlikely in those cases, because here the online Q function is going to be moving. So at least this gives us a little bit of some glimpse into this where, okay, the Polyac averaging may not converge, partly because the target is always changing as well. So in terms of this converging and coming up with some type of contraction, this is what starts to give us at least a little bit of pause to think about this more. And there are many, many papers and researchers that really dislike having target networks, partly because of some of these issues. So you'll see papers that try to remove them entirely. We even talked about one for PQN in the last class as well, because they just cause more, it adds more stuff to the algorithm, and it technically adds stuff that's not going to be like well aligned with being able to have a good contraction. Okay. So this was also still some of the details where this update here is, still never a version of the online Q function parameters that existed. So if you wanted to do something like, if we remember some of the stuff about doing like policy iteration, where you make like a good step on learning a value function and every value function is a little bit better than the last one. That's not entirely true here. Okay. All right, so now for some of the weird and ugly details, which you probably won't see in really any of the papers that you read about these methods. So one of them, which was a real problem when this, like this general DDPG algorithm was started, was dealing with basically the output layer for the action distribution. Because now you've got this Q function, the algorithm is basically training this Q function and you're passing a gradient to update the policy parameters for the actual policy. So one thing that would happen really way too often is at some point the policy parameters and the outputs would start to like go off into infinity. Like if you get one gradient from this not very well formed critic, it's computing the Q value, could then result in a really large change in the actual output of this policy. So if we kind of like remember a little bit like the stuff we talked about for PPO, being able to have like some constraints on how much the policy distribution changes, so things don't go, like too wild or basically too much change happens at once. The same problem at even a much worse extent can exist for these methods. And there were a couple of different ways to be able to overcome this. So basically part of the problem is there's really almost uncontrollable size gradients that could exist here. If you randomly initialize the network and start computing gradients back through it, if you're lucky, they don't grow too much. But Q functions end up being kind of like sharp and peaky and can cause really large gradients. One of the methods that a few papers used was actually to just basically add like a regularization cost to the action output. So it can't get too far away from zero. So this isn't to the parameters on the network. This is literally don't make the output of the network too far away from zero. Because anything that's really far away must likely be nonsense, right? One of the other slightly less like strong changes that can be made is actually to get around this by changing the activation. So here you can use a tanh activation, which is also bounded between -1 and 1. So now you know the output of your action network is always going to be between -1 and 1. And then you can just map those back to like the joint limits on your robot or the speeds your robot arm can move. And at least some understanding for like the scale and speed of the actions that are outputted. And then this one that was an interesting paper is actually squashing the gradients. So instead of adding an activation, as the gradient starts to basically encourage the distribution to get further, like away from zero and more towards one, basically reduce the size of the gradient kind of inversely. So that as it gets further and further out into kind of crazy land, basically reduce that gradient almost down to zero. Okay. And then some of the last methods that can also work well is you could try adding dropout to this, since it's a good way to maybe not overfit the actual input to the Q function. That also seems to work okay. And still this problem, which we'll basically talk about for the whole second half of this lecture, is how to deal with these problems as these networks get bigger. As they get bigger, the possible changes in outputs can like happen even more and be even larger. And then basically how to deal with those challenges. Okay, does this make sense? This seems sort of like mundane. It's not as technical, but it's kind of in the weeds and the details. But very often at least when you go and look at some of the libraries for like TD3 or SAC or maybe DDPG, if you found a really old library, they're most likely going to be using something like this as the activation layer at the end of the network. Do not change that activation layer or nothing will work. They should have probably at least one of these methods to reduce the network from just going off to like positive or negative infinity. Okay, clear for now? Okay. These are all this is a really good segment in what'll be a lot of stuff that'll be included in these slides, which is just sort of like, here's the math, here are the details to make sure that math doesn't essentially get outside of the fenced in area that makes sense. Okay. Ah, all right. So then how should exploration noise be added to this algorithm? DQN was kind of easy. Basically, just either pick the best action or choose one at random. And since it's discrete, one can be basically chosen at random kind of whenever, and it still can work out well, but you can't really do that for this more deterministic policy. Um, Technically here, this is a bit of a weird aspect about these algorithms because these are deterministic policies, so not stochastic policies. So really, the choice of noise is not, so determined by the policy, but it also means in many ways any type of noise can be added, almost any type. So if you've got your favorite exploration method or your favorite type of noise distribution that you're familiar with in continuous spaces, it could be used here. But here's a couple of the more common versions. So one is, it's very common just to add some Gaussian noise to this. So before, where basically mu here is just the mean of some Gaussian distribution, do some hyperparameter tuning, figure out a good sigma, and then leave that for being able to train your algorithm. So that one's not too bad. Pretty common. It's nice because now the policy doesn't have to also figure out the noise distribution for exploration, which is actually kind of a complicated hyperparameter to figure out. There's some other versions too. So the original version for the DDPG paper used Uhlenbeck Ornstein noise, also just often called UO noise in many papers. And this is also really connected to Brownian noise. Okay, so how many people are familiar with Brownian noise and have a PhD in physics? Okay, just me, and I don't really qualify for that second part. But Brownian noise is very similar to Gaussian noise. It's just allowed to deviate. So Gaussian noise is basically being able to add some distribution of noise over this mean. Brownian noise is allowed to deviate from the mean with a little bit of momentum that can kind of go away from the mean over time, but it also always returns to the mean. So it's kind of like it can deviate a little bit more with some noise over time, but it always trails back to the mean. So now it can kind of explore more than just around that mean with some structure. The idea was, well, in this case, if there are more complex paths for the agent that they need to follow during exploration, it's possible that Brownian noise will help find those paths a bit better. And this was definitely used in the DDPG paper. It can technically be used for a lot of off-policy algorithms that we're talking about today. Okay, does that make sense for Brownian noise now? If this is sort of time going this direction, and what is this? I guess sigma, something going this direction, the amount of noise, and then just do that on many dimensions. So you'll likely see a lot of papers with many different types of exploration noise if that's the sort of thing you're interested in when it comes to RL. Okay. So that's always a bit of a challenging aspect here is like figuring out which algorithm to choose. Because, so we talked about having discrete algorithms versus continuous algorithms. I won't say that these like groupings are entirely made up, but when it comes to like the robot or the agent that is going to be controlled by the algorithm, we have a bit of a choice about whether or not we want to convert that environment into discrete or continuous actions. So it really depends on like a good basically recipe is going to depend on like the size of the action distribution. So if the action distribution is actually pretty small, it can still be approximated with a good like discrete model. So if the agent or the environment only has like 3 actions that are continuous, there's actually not a big difference between them. Very much like what you did for homework 2. you can basically approximate this distribution really well with the discrete distribution. In fact, if that distribution has modes in it, it's likely that this policy that's been discretized will do even better than using, just something that's using a continuous distribution, because at least when we're using Gaussian distributions, they're very mode seeking. So if your algorithm happens to find the optimal mode, you're in luck. If not, you're out of luck. But that's always a bit of a choice. And that's also why I included that in homework too, because it's sort of like, think about this process a bit more. Actually, a lot of robotics papers kind of shift from continuous distributions for actions to discrete ones because they're easier to optimize. They're more deterministic in some ways, and you can often use larger models. It's maybe even one of the reasons why like transformers are becoming more popular than LSTMs, because transformer is actually a big, giant discretization. Big enough though that it approximates the continuous problems at least somewhat well. Okay. And it also matters a bit whether or not your distribution is multimodal. I think we've seen this image before. So think about the distribution here, where one thing that can be done is you can actually make a couple of action distributions that come out of your policy to maybe handle one or two modes. There's certainly a number of papers, even this one that I was showing for a bit. It's got 4 actions and then 6 action parameters. And then depending on how those will learn, it'll select like different actions from the other ones. So it's possible to have a policy that would be like mu0, mu1, mu2, and then train all of those. And then I suppose here you'd have Q1, Q2, Q3 to figure out which one of those policy action distributions to choose. At least this particular model will cover those 3 modes. Okay. Great. Does that make sense so far? I think if you've now survived homework 2, you're kind of get a good understanding for this particular problem a bit more. But just remember, this is a very useful tool. Okay. So upon one of the challenges, though, is like basically somewhat long history, depending on how you define long these days. But I think it's now been almost 10 years, I guess 8 since DDPG was published. But the real problem of figuring out how to deal with kind of like, we call it sensitivity in a mathematical sense of these networks. Just the fact that, this Q function is now going to be taking inputs from some policy, and how basically sensitive is that Q function to like small changes in the actual inputs from that policy. So this can cause some problems for exploration, but definitely actually in the training process, because we really want the Q function to provide good gradients here. So then what can be done to this Q function in the training process to making like the optimization landscape a bit more smooth? So one of these was introduced, for example here, because this, like even if this is computing a gradient and it's using the target network, this target network may have never actually seen this generated action like ever in its existence. So it is very likely that when those Q values are being computed for those targets, they're almost all out of distribution. Because remember, the actions that are generated is still mu, given like some normal distribution and sigma. So that means it's unlikely it was ever exactly that action. And deep networks are sometimes very sensitive. If you don't give exactly that thing that was before, it could be kind of unbounded in the difference in the output that occurs. So then one normal tool that can be used here is basically add noise. Force the model to become a bit more robust such that inputs at that particular spot and then plus a little noise all end up having the same output. So this just sort of means it's enforcing a little bit of locality in the actual like samples that are coming from that particular environment such that they all map to the same target value. Remember, that's sort of the idea here is now this is going to be used for the Bellman update. So you can take the original network, add a little bit of noise to the output, And this can be sampled a couple of times, really, and then include that in the batch. And then everything that's at that location plus a little noise should all really have pretty much the same Q value. There's definitely a couple of assumptions going on in this, but this already at least provides a little bit more structure. Okay, does that make sense? Certainly, one of the assumptions here, though, is almost in this continuous control domain, things are kind of smooth, such that, like the Q value of something really near itself and that's a little bit different should be about the same. This isn't always true, but, like in the Majoko environment that people evaluate these algorithms on way too often, it's pretty smooth and true there for the most part. It gets a bit more complicated whenever, like the simulated robot is touching the ground or not. Those discontinuities are more where Q values change quite a bit. Okay. So this is a very small change. So DDPG was just some other details for training, and now this is just really just this part. Add some noise to this algorithm. And it's kind of surprising how much this helps. So if this was DDPG, here is the orange. And there's a little bit more to TD3, but really this whole concept kind of a lot related to that noise. And then now TD3 up here performs like significantly better across all of these different environments. I think with one exception from some of the details here. So this is why you should, if you're doing some off-policy learning, you want to be more sample efficient, look at TD3. I'll talk about SAC in a couple of slides, but this is a good start. Although I think these days there's like a TD7 and probably incrementally growing numbers of these algorithms that have a few other changes. They do help the overall algorithm scale up a bit more. All right. So I wanted to ask a different question about this while we're looking at this graph. And it's about this inverted pendulum environment. How useful do we think this inverted pendulum environment is here for evaluating RL algorithms? So for example, how many would want to keep using this in your paper and would trust the findings of people that compare over inverted pendulum? Not too many? Got one? Okay. So no, it's good. There's a bit of a challenge here though, is like in many ways, all these algorithms are now starting to look really similar. Some of them are a bit noisy, but they almost all have this curve. Like start out learning, they all learn pretty well and they're done. So it's almost like this environment is now easy. Like all the algorithms can be compared on this or run on them, and they don't really take a lot of challenge. So it's sort of like when I look at this particular figure, if they all look the same, it's not giving a lot of extra information. So now this is just like a bit of a reminder and a bit of a discussion of at some point, I'd hope anyway, like every environment actually becomes obsolete and we need to like keep moving on. In this case, I mean, inverted pendulum is kind of simple, but now that the algorithms learn so fast, they all look the same. So the community needs more complicated tasks, basically, so that there's now a difference between the algorithms that are run on them. Yeah. Mm-hmm. Mm-hmm. Yeah, that one's a bit more complicated. I think inverted, so that's double inverted pendulum. So inverted pendulum, I think, is just like this. And then the idea is to get this pendulum pointing up and you're good. It's not very complicated of a task yet. Well, no, it's not a very complicated task in order to be able to get that to work. It was at least good for maybe debugging, can my algorithm converge? Because that was absolutely a problem for many years, sadly. But that was where the research was at. But now a lot of the algorithms are doing much better than that. These days, they at least kind of train pretty well on most environments where the algorithm is just kind of like put on that environment, plus or minus some hyperparameters, but still works pretty well. So this, I mean, this can happen for robotics too. There's a reason why we had a bit of that discussion early on about like, what do we mean by generalization? Because if the task, and I know at least most of the people in the room here can see my pen, but if this is the starting position for the arm and the task is to touch the pen, it's not a huge challenge in order to be able to do that. So we should kind of think about this always as kind of a moving target in terms of like, now we can increase task complexity. And then now we might need to like add more environments onto this. And these days, actually, we're getting some pretty good progress in here where environments are becoming like a little bit more complex, a little bit more realistic. Here, all these were half cheetahs and stuff, so they're all just these weird capsule things that look nothing like real robots, don't really have any consideration for friction or the weird dynamics of motors. Over time, we slowly make these a little bit more accurate. But I wanted to make sure to have that discussion. Does that make sense? Yeah. It's the same reason why, we also do school. There's a reason why we're not still doing addition in this class. And now, you know, instead assignments like homework 2 are given, which are way more work and require a lot more information. Also because it's good prep, because it's likely, when you're interviewing for jobs, you're going to get similar questions about that stuff. And now you'll already know how to answer those questions real quick. So it's good practice. Yeah, so we already covered that. Yeah, part of the challenge here is still these are converging and they're training okay. Technically, they might have some challenges with doing exploration. So this is where I'm going to introduce maximum entropy RL. Yeah, still time. Okay, I guess this is now another physics question again. How many people are really familiar with information theory and entropy? No? What do you do in your sleep? I don't know, just joking. But entropy is just it's actually interesting. Often people think of it as noise. But technically, when entropy was first thought of, it was actually in the realm of trying to figure out how to communicate messages while still handling some amount of entropy. If you want to go back into a good history. So this is actually it's kind of originally the inverse idea of like how much information is contained inside of this event. If there's not a lot of information, it's most likely just really noisy. But basically, this is just sort of a bit of computer science and information history. It's better defined as basically, as the amount of information needed to take the noise away from the actual process and then be able to just recover the signal. And if you want some more good like bedtime reading that might help you go to sleep, you can go and read some of this work from Shannon, which is actually like really important to the development of computers, just like at all. Otherwise, we wouldn't have any good like solid state deterministic systems to program. So maybe a good read. I certainly enjoyed it quite a bit. And it's just always this process, basically just, x log x for determining what the entropy of some signal is, at least when we're talking mathematically about this for a discrete distribution. Okay. All right. But now we're going to use this as a way of thinking, all right, how can we induce some entropy into the policy exploration process? Partly here so that we know that the policy is like covering the state space with some good amount of entropy, or at least the action distribution. And it should explore better than just adding Gaussian or Brownian noise. So the whole idea is to kind of bring back how to perform good exploration in a structured way in the actual loss and training for the policy. So if this is the RL objective that we all know and love, then basically what can we do to add entropy to this? And we want to add entropy because maybe this particular objective gets overfit a little bit, where if the policy ends up exploiting this objective too strongly, it might not actually find optimal policies. And this is something that like deep networks also have a bit of a brittleness too, because they tend to have a lot of memory essentially. So it'll overfit a lot of early exploration and data. So it often can help to include a bit more encouragement for the policy and the optimization to include exploration more in the actual training process. Okay. So so one way to be able to do this is if we kind of like basically exponentiate the Q function, this can be a model for the policy distribution. And then from this, the idea is to use what's called maximum entropy optimization and then construct an RL algorithm from this. So just a little bit of an aside. So maximum entropy, kind of the optimization is basically, find a model that describes the data with the fewest assumptions about that actual model. And this can be useful for a number of reasons because you really don't want to like overfit the data. It's bad to make assumptions in the model too, because it's most likely going to be brittle to those assumptions. So again, if you want some more bedtime reading time or bedtime reading material, you can go check out a few of these papers on these optimization methods. They're becoming more and more useful, and even used a lot more these days for different types of optimization. Okay, so at least though where this leads to for maximum entropy RL is basically, so this part, probably shouldn't use that exact symbol because that'll get confusing. Maybe I'll do this. This is still the normal RL objective that we're all pretty familiar with. Now, in this case, what's being added is, well, now there's going to be this entropy term where we want for the algorithm basically to have some amount of structured entropy over its distribution. And to basically figure out how to like induce and like use this exploration for the policy to be able to explore a bit better. And then here, the way this ends up being, adjusted so that we can actually use it for QLearning. If this is now the Q function, it's sort of normally based off of that. We basically use the softmax process, and now our policy becomes something like this, basically figuring out how to estimate this particular distribution here compared to the actual policy, and then trying to keep that kind of balanced. This part does end up being a bit tricky. And I mean, so this is really an example of the SAC algorithm, like the soft actor critic, which to be honest is kind of like one of the weirdest RL algorithms. It's also the algorithm that is implemented with the most variety in the community because people, for different algorithms, they will use just a Q function to be able to do this estimate. For some of them, there's also a value function that helps control some of this a little bit better. So there are a lot of slightly different variations on how to be able to implement this well. So just be cautious when you're looking into these papers, or if you're looking at some of those code or implementing yourself, there are a few different ways in order to be able to basically learn now what is an estimator over these two objectives that'll still work well. Okay, but of course, let's look at a video to kind of understand more what I mean, and hopefully, oh my gosh, no ads, a miracle. So the idea here is like, so now exploration should be more distributed over the distribution of possible trajectories. Here you can see the little ant here on the right with a kind of purposeful block put there that would kind of like cut right across the middle of the distribution. So if the agent ends up, in the initial part of training, exploring this upper part of the room, very often with DDPG, it's going to get stuck there because it's not going to really have much of an encouragement to leave that kind of peaky distribution of following its actual data for what it's collected so far. The idea in soft Q learning is to help it not overfit like those peaky exploration distributions early on. And so it should result in finding more optimal policies. Given enough time and given enough whacks of your head against the wall for figuring out the hyperparameter tuning for SAC, because there's a few more parameters now for this algorithm. Okay. Does that make sense? Questions? Pretty good. Okay. Great. So those are really two of the most popular RL algorithms that are used, especially for off policies. TD3 and SAC are used quite a bit. Right, we're back here. Yeah, and then a little bit about a practical algorithm to be able to do this. So there's at least one part, a reparameterization that often needs to be done because There needs to be a way, because now basically a policy is being trained. It's not totally well, we want it to be some type of stochastic policy. So often in a lot of these SAC libraries, a version of the reparameterization trick is used such that that policy now depends on some other function that is also adding noise. And that is a way then to introduce some of the noise into that policy training process so that it'll actually kind of explore over itself and be able to do this now somewhat maximum entropy optimization over the model. And then, yeah, this is the part that many people still have a hard time with, where it's nice to be able to add this entropy as a way to think about it as an optimization. It adds one more hyperparameter that can be kind of problematic to figure out how to optimize over, because basically how much entropy that the pol should be introduced in the policy really depends on like the average rewards the agent is going to receive in the environment. So it's a bit of a more larger of an unknown to figure out. At the time, basically a lot of the authors can do a somewhat like tricky balance where you could train one policy kind of without the entropy in it at all, such that at least you can start to learn how, like, what is the Q values that'll be received throughout the training process, and then reverse engineer a good lambda here such that the entropy only contributes about 10 to 15% at most of what would be the overall value for like the best Q function. So you can kind of reverse engineer this hyperparameter. Although there's still a couple of, you can do this now, at least versions of SAC these days do this in an even more complicated way, where now this hyperparameter can actually be learned. So you could have a setting that says, there's sort of like a new parameter that says the entropy should take about 10% of the overall objective. And now this optimization can figure out now what should that lambda value be right now during the optimization with a little bit of adjustment in order to be able to make this like 10%. The entropy should now be 10% of the overall Q value, something like that. This is a version of being able to do something like dual gradient descent, where you can make some steps on the original objective, which is basically this, and then do another step on figuring out, okay, what parameter is best here. This is also somewhat connected to like finding a good Lagrange multiplier when you've got two objectives you're combining, if you're more familiar with that. Okay, does that make sense? Any questions about SAC? No, we're all really happy with that, and we hope to never have to program it from scratch ever. Well, I've got good news. I dropped that from the homeworks this year, but that's also why I put in homework 2, which wasn't from last year. So you won't have to program this year. You'll still do something a bit similar, but it'll be much more for offline RL than it will be directly having to code up SAC. Because to be honest, SAC is probably the hardest RL algorithm to code up from scratch. It has the most moving parts, the most complicated, probably optimization in order to be able to get working, and some of the more annoying hyperparameters. And all those weird issues with having to deal with the policy distribution, like shooting off to positive infinity and basically being unrecoverable. So I guess that was a bit nicer this year. All right. Let's see. All right, let's stop there for now and take a break, because next we'll get into now how to scale all these methods and kind of more into our paper discussions. And then, yeah, we'll start again at 2:30. Mm, we did test it in hardware and in. Mm. I mean, yeah, but in some ways, this is a completely different task with different objects, a different robot arm, and a different background. So that these details do end up mattering a little bit. Well, a lot, really. I think it would, but at this point, the largest limitation is just we're only training it over a small amount of data. So if we like trained exactly what you've done for your homework assignment, but trained it over everything that's in the OpenX embodiment dataset, I think it would then end up doing an okay job. Yeah. But right now, like even if you look into the data set that I created, which only ended up being like 100 trajectories, of that, there's really, I think there's like 10 trajectories for every task. So there's actually only 10 different tasks in there for the language model to generalize across. And that's really what the T5 model is meant to help for. Hmm. Without anything else being added to like the current version of Octo. Uh, the old rule is you really need about 50 trajectories ish to have enough data for any single task. So that would, and if we wanted to generalize well across a number of tasks, I would say it would need at least 100 different tasks to, in the best case, be able to generalize a little bit. Yeah. Yeah. One way to start here is if you look at the perceiver actor paper, they had a bit more of a structure around the way the sentences were specified. It was always of the structure like put A on B, basically, or something like that. So it kind of greatly reduced the diversity of the goal descriptions, and then they didn't need nearly as much data. So that's going to be like the minimum amount of data, where I think they did collect about 20 trajectories per task, and then it generalized okay with a lot more visual diversity. Um, but it's still a little bit of like a difficult question to answer of how much data would be needed to get this type of generalization. Technically, that's almost impossible to answer, especially when we're only using behavior cloning. Because more data doesn't always mean a better, well, despite the scaling people that might exist in the world, more data is not always better, especially if none of the data includes a solution to the task. All the data technically in the OpenX embodiment data set is kind of like a solution to a task. So that's at least a better outcome. Hmm. Yeah, sure. Mm. I guess you're also welcome to try some of the other tasks in the simulator because we picked the put carrot on plate because I believe that's one of the tasks in like the data that I put aside and parsed. But you can try some of the other tasks that are both in the simulator, and there's not too many of them, and then the ones that were in the data set that we trained. Yeah, that'll help. Mhm. Okay. Everybody still awake? Pretty quiet in here. Maybe I'll bring noise to the next class or music or something. Maybe I'll play elevator music during the break time so we can all kind of chill out a bit more. Who knows? Yeah, I know it's been a long week. Hopefully everyone's looking forward to the reading week, which is not next week, but the week after. So keep that in mind. Uh, okay. So a lot of that was about algorithms, a handful of math, which still requires a lot of effort to actually get working well. So kind of like the next set of slides here is all much more about, all right, how to combine these methods, make them scale well when it comes to basically using deep learning and deep networks. So one of the first problems that shows up for these algorithms is early overfitting. So in this case, basically whenever training networks in these problems, the dynamics of the training process are fairly complex. One of the earlier pieces that was at least identified in a bit more of a better structure is understanding what is called the primacy bias. So this is just like early on in the training process, if the Q function is being trained over the policy, it's being trained over some batch of data that's seen so far, it can, like in a form, start to overfit that data and at least overfit such that it's not going to be able to learn much about what comes up on later in the data. And this is basically a form of this like primacy bias, which is kind of a concept of, early on, just the agent ends up becoming a specialist or like very good in that early data. And it makes it weak in order to be able to learn stuff that comes along in the future. So this is a problem because this early fitting also can cause a lot of divergence. Now, as the agent goes to train later on in this data, um, this divergence can start to incur because it's basically the data in the future is going to look more and more off policy, and the old network basically isn't having a good time being able to adjust its distribution towards this new data. So basically, it's kind of like the Q function gets pretty out of date, and the action policy might still be changing and collecting new data, and they get really out of sync with each other. So one kind of like I'd actually say one brutal method to be able to do this is basically to use policy resetting. So this is you can either reset part of the like network for the Q function or for the policy, or it can actually reset the entire thing. And this ends up helping a fair bit in terms of actual performance. This at least helps avoid this primacy bias challenge because here it's sort of like as the policy or Q function learns for a little bit, it starts to overfit, maybe get this primacy bias, and then essentially reset. So like generate a new set of network parameters, just like as if it was a fresh new network, and then kind of introduce those parameters into the network. So it's kind of like starting fresh from that point. So there's no more bias. It doesn't actually model the current distribution of data really well, but that's not the problem at the moment. The problem is it overfits this early data and then can't kind of get into learning the new data that comes along over time. Okay, does that make sense? Sort of this tricky and somewhat annoying fact that the policy is kind of iterating through many different distributions of data. It's going to essentially can overfit the earlier versions. So one of the reasons why this is also really helpful to pay attention to is because we want to be able to make these algorithms more sample efficient. And one way to be able to do this is if we go back to some algorithm here for this one, for example, is it would be great if here there could be another for loop that basically says now for every action that's taken in the environment, how many update steps can we do on our model? And it's just the idea that the policy and algorithm should be able to make a lot of update steps. It should still converge, although the short story is when more update steps are added, essentially over this chunk, this starts to diverge faster and faster, which is a real shame because this is really like where we can maybe get sample efficiency to work well, like collect data, train over all the data really well so that the algorithm captures the best Q function and policy. But using this logic actually causes the algorithm to diverge, not to do well. So this means, and this is kind of like the next couple of slides and papers we'll talk about, is like figuring out how to basically put a type of for loop here and increase this quite a bit such that things will not diverge and better sample efficiency will be achieved. So one thing that helps here is actually this resetting behavior. So here in this process where if it's just normal SAC, and this is that replay ratio, so how many times an update over the model is performed per every step in the environment. As this increases, yeah, SAC becomes more and more unstable, performs worse and worse over time. Using these resets, where basically if some portion of the network, let's just say for at the moment, like all of the network is reset, but the replay buffer of data is still always kept around, and the policy just trains over that again with that data, is now actually going to result in better and better performance as the replay ratio starts to go up and up. There's a bit of a detail here where if this goes further and further, it actually starts to still trail off, but this is still good progress in being able to learn from this. This makes sure that, okay, great, our algorithms are not diverging. If we can increase this replay ratio, this means that we can essentially have the agent soak up all of the data that it actually collected already. Because we talked about this a bit earlier on in the class, where like a policy gradient method can like kind of do 10 updates on the data before it essentially starts to diverge or can't learn anymore. So we really need algorithms that if data is collected in the world, and for example, if there is an optimal trajectory inside of this data set, it should just be like learn that, like train over the data as much as possible in order to be able to like incorporate that best trajectory into the policy, because it has to go through the Q function here and then into the policy in that process. But what might happen here with current RL algorithms, because they essentially need to like revisit that same thing maybe 100 times, it means not only does the algorithm need to stumble upon the optimal trajectory 100 times, but then also needs to train over it very carefully to learn that. So it's surprisingly sample inefficient in the way that it's currently learning. So these algorithms are making nice steps of progress along this of being able to, when any data is seen, like train over that pretty extensively to make sure you learn the most from it. Kind of like maximizing info gain from this new data. Yeah. Does that make sense? I mean, in a short sentence, it's just learn as much as possible from any trajectory that is collected before throwing it out. Right now, it's actually kind of a struggle with RL algorithms. It works much better for behavior cloning, but there are different problems there too. Okay. And this is our, what's this? Oh, so this is Atari and this is the DeepMind control suite. So the algorithm works pretty good for both of these. We're just doing these resets. There's still a bit of this question for like, okay, how often should these resets be performed? Because this is still what I like to call a pretty blunt instrument. It's kind of like, it's not very surgical and nice. It's basically kind of come in with a sledgehammer, destroy all of the knowledge in the network, reset it from scratch and learn from there. So it's still kind of wasteful there quite a bit, but you still need to figure out like, how often do you reset then given the data here? So at least here you can start to see these are number of agent updates versus IQM. And then I guess that wasn't quite included here. So this is environment steps. So here you can see that as the number of environment steps increases, this is starting to have a slightly better performance. So the learning performance still improves over, given the number of different parameters that are learned here. So this is one of the earlier pieces, and basically this started kind of a nice tree of a couple of different papers of figuring out how to improve on this problem of being able to like absorb more from the data and do it well. So this is kind of like the simple resetting that's currently being used, which is just current network parameters, some totally random noise for the most part, 0, and this is just basically, I guess this really isn't in any of the code, but this is basically like torch.like init whole network generates a whole new network, and then you kind of just push a portion of those parameters into the new model and then learn from that. Okay. And this is just basically it as an algorithm. So all this is still the same, nothing new up here. But now here, this is each one of these W's is essentially like reset a network from scratch and then contribute a few of those parameters up to some lambda value over to the current network and do that ever so often. I think in this case, it looks like it does it all the time. There's been a couple of different papers. Some of them do a little bit of noise at every step. Some other ones are kind of like the target network for DQN, where it's train a policy and then basically reset a large chunk of the network. These have kind of been good for different types of environments. Yeah.
And this early overfitting stuff happens even PDs, like the classic
Yeah, because it's a different type of overfitting. It is that it's overfitting the current data distribution. So even if you use dropouts, it'll still technically like not overfit as if you held out some data from that same data distribution. Yeah, because the problem here is, well, now that data, the whole data distribution is going to change. So it's not that it's overfitting, because in supervised learning, the problem is overfitting any individual point in the data set and not doing that too much. Here in RL, it's like now it's overfitting the distribution of data for that. And we don't want it to become too fixated on that and like be biased to that, because in the future, it's going to be a different data set. It's kind of how we like break the analogy for using supervised learning in RL. It's also why the terminology for bias versus variance in supervised learning does actually not transfer to what people normally use in the RL community. By bias, we kind of really mean like overfitting an early data set or a reward or an early reward function. And then variance is just like variance in the policy gradient estimate, not like variance over the model parameters of how it fits that data. So careful of that one. That's also a common interview question, it seems, from people I know. But yeah, that's at least why it makes this a bit more difficult to deal with. Also because we really don't know how much that distribution is going to change, especially as we get into more fun and cool environments to be able to like train a policy over. Yeah. It's also one of the reasons why I suspect we're still not good at making RL algorithms that do well on things like Minecraft. Just the sheer change in the data distribution is so large that the primacy bias is basically going to, ruin any hope of ours for the algorithm to eventually optimize a good policy, because it'll be so essentially like overfit to earlier data, it can't even learn from the new data. Even if it wanted to, even if it's there, it won't learn. That one's a bit of a hypothesis, but it's a pretty strong one I've got these days. Okay, other questions? Okay, we're going to get into this a bit more. Now we go down the rabbit hole. Oh. Okay, so then there's a lot of other recent improvements that basically build on this. We'll talk a little bit about being able to scale the network size. These are basically the papers that were like assigned for this week. We'll study a bit about the learning dynamics. I didn't end up going into many details about continual backprop, but if you really want to get even more into some of the learning dynamics, you can have a look at this recent paper that's actually in Nature for figuring out, like, if you remember way back, we had that slide that was basic QLearning that was just like collect a single data point, update your Q function, and then go back to learning. And that paper basically is able to achieve a version of that. Well, this plus a new paper that also says like streaming RL is starting to work. And this is where it's just the agent is just getting data like one data point at a time, doing an update and learning and working, which goes against basically everything we've talked about for getting deep learning to work. So nothing is IID. It's probably pretty problematic. Gradients don't, your batch is teeny. There's going to be all sorts of like primacy bias issues, but it still seems to work for now. And the idea is people seem to learn that way. So maybe we can make an algorithm that fits that learning style. And then we'll talk a little bit more about representations. All right, so let's get into the first one of these. And this is one of the ones I want to talk about. So this is bigger, better, and faster. The idea here is really, um, if you remember for like the DQN papers, or seemingly almost anything that was based off of DQN, almost always used this network style, which is a 3-layer convolutional neural network, one dense layer, and then the action distribution. And that became like the paradigm in learning for a while. So the problem isn't really with this specific network design, but it's just, can algorithms be made to use anything bigger than this model? The short story was like before this paper, not really. They would all be pretty unstable, maybe partly because of this bias, like primacy bias. So now if you have a bigger network, it kind of gets stuck in this primacy bias much faster, potentially, in this process. So what was basically what could be achieved here is now being able to scale the parameters of the network and still being able to maintain and actually being able to improve some of the performance that can be achieved in these environments. And this is on Atari. So this was also introducing a slightly new environment setting. Although, I mean, okay, so hopefully my bias or my non-favoritism towards Atari benchmark doesn't like be introduced too much into this class. But basically the Atari benchmark was used for a while. Then a bunch of algorithms were doing really well on it. So people were like, well, why should we kind of care about these benchmarks anymore? And then somewhere someone thought, well, how about we just make Atari, but you only have 100,000 steps in the environment before you do well. So I guess people just really like Atari and get so fixated on it. They'll try to make it last however they possibly can, instead of going to things related that look anything like the real world and the real world dynamics. But the idea for this Atari 100K is it takes about 2.5 hours for the average person to become kind of good at any of the Atari games. So then that corresponds to about 100,000 steps in the environment. So the idea was to make human level Atari with human level efficiency is learn to be as skilled as a person with the same number of steps in the environment. So that was at least the benchmark used for this, but the goal was still being able to do this with a larger network and achieve that. So a number of different like design choices were tried in order to be able to get this to work. So this is basically the ablation analysis in the paper, where, being able to adjust the discount factor didn't help or change a lot. Being able to use, let's just say SPR is kind of like a representation inside the network did help a bit. Things that seem to be the most important are like being able to control like the amount of like end step learning in the algorithm and how much that ends up adjusting how things actually learn. And then here, this one, since we've already been talking about resets, is being able to do some type of reset ends up helping quite a bit. This was an interesting version of resets that's used in this paper. So it's not resetting the entire network. They seemingly did a fair bit of analysis. In the paper, they're really only resetting, I think, the last 2 layers of the network. Okay, because the detail I left out is in this case, they're actually using a ResNet for the parameter model at the end. So in a ResNet, you can just like add some more ResNet layers, and then you can get more parameters for your network, so you could grow that over time. So in this case, resets were just being added to some of the later layers in the ResNet, and the earlier stuff was still left the same because, well, there can be a couple of different reasons for that. But this is what ends up causing some of the better performance. Okay, does that make sense? Any questions? All right. So if you do full resets, that actually seems to kind of hurt performance a bit here. And this is like reset of the entire ResNet, which shouldn't be too surprising, right? I think part of the idea behind these harder resets at the end of the network is, well, the ResNet is learning stuff related to just doing perception in general in the like Atari environments. And even at that, like perception kind of generalizes across tasks, being able to pick out items. So primacy bias in the earlier part of the ResNet, not as much of a problem. Later on in the network, Now it has to make decisions and maybe change its policy distribution about which actions to take. That's where primacy bias can become a larger issue. It's like less generalizable and transferable information. Yes. Yes. Adding the resets ends up helping, but they tried two different versions of resets as well. But it was a kind of very specific because the previous paper was, like I was saying, kind of blunt and just like using reset everything. Now they're being at least more, a little bit more surgical about which areas to reset. And even from this, as we'll go into some of the next papers, actually people stop using resets a bit as well because they're a related challenge, but maybe not the real issue to get to. Okay, other questions? Okay, so then so we still want to kind of understand this problem. So we were calling it the primacy bias. In general, if you're looking at papers that are doing anything related to continual learning, it's usually called plasticity or forward transfer, just like how well does your model work that the agent has to be able to do well on like future distributions, future tasks, future reward functions. And if it can have better plasticity, it means that the agent is good at being able to adjust its own model to stuff, different tasks it sees in the future. It seems that there's a couple of important pieces. So one, the loss landscape is really important. And this basically means that, so far we've only really been talking about like one task, collecting some amount of data, but that doesn't mean that the loss landscape can't change. So in this case, it's basically like, just think about this case where the agent is going along its environment and it, I don't know, finally solves the task and it gets a reward of 1,000 or something like that. This is actually kind of a weird problem when it comes to training the deep network, because now this gradient for this thing that is seemingly awesome for the agent to learn is 1,000 times the size of any other gradient that it's seen so far in its whole training process. So if anything, this kind of looks terrifying in terms of a like gradient optimization scheme, because it's going to come in and might wipe out like all the parameters in the network and way overshoot actually adjusting itself towards that new like trajectory it found that reached that. So that's another kind of more detailed issue about how to get this stuff to work. So here, though, in this particular work, it's going to do this a bit more explicitly, and it'll actually be switching between tasks. So it knows when the reward function is going to change, even though the reward distribution can change seemingly at any time during training the policy. So here, from these changes, you can kind of figure out why do these different issues cause some other change. But then here's basically an example of this. And you should go and download the new set of slides because I updated these this morning if you've got a version that doesn't have any of these papers, just in case you want to follow along more. But you can look over here where like this is the accuracy for the actual model. And then what starts to happen, in part of the paper, they were studying dead units. And these are the task boundaries. So the basically after the task changes a few times, for this blue model, it ends up like starting to perform really poorly, partly because of this change in the loss landscape after every like individual change for each task. So this just does not play very well with the really careful ball of statistics that is basically a deep network that we need to like gently nudge towards finding an optimal policy over the training process. Here, there's all of a sudden large changes in the reward that cause large changes in the Q function that needs to be trained, and then really large gradients for the policy. So it's all, basically it should set off some red flags in your head. It's like, okay, all of these things, not good for nice, good convergence or policies. So this is what I'm getting to here, where the reward can lead to changes in the average gradient size. There's also changes in the dynamics that can cause changes in the state distribution, which can be a bit out of support. Okay, does that make sense? It's kind of a detailed, somewhat complex aspect of being able to do RL. Well, no, being able to do deep RL. This doesn't really exist nearly as much for RL. It's the deep learning part that makes this problematic. Yeah.
So I was thinking, so I guess the difference here is, so if you do the reset that I already have, then yeah, so you're resetting your network to some like some noise. Where here it's like, I guess your network has like a different prior, like starting prior week. So that's my here. I guess the difference is the optimizer is still kind of memory, I guess. What if you reset the optimizer? Not the kind of the same as you reset the network, but then you reset the network.
That can help because yeah, that is part of the source of the challenge here is like if this is being optimized with Atom, Atom has also been collecting some statistics where it's trying to figure out how to scale the size of the gradients during training, and it should converge over time. And then if you suddenly change the reward function, then the statistics for Atom are basically probably useless. In this case, I do think they also did some resetting for Atom, and that didn't end up helping a lot because it's still about like that distribution of rewards. And at this point in training, the policy network has gotten pretty far away from its random distribution. Like it's in its distribution in the beginning. So it still has a lot of its own memory about the distribution it wants to output. So even if at that point, like if you used SGD normally, like the whole time, at that point, there'd still be a large change in the gradients that happen. So at the very least, you'd have to like step back, maybe change your hyperparameter for learning rate for SGD and adjust it a bit there to make things even more stable. But yeah, this is we're kind of like, this is the onion of deep reinforcement learning, and maybe I'll use the symbolism better next year. We kind of like unwrap, this was the algorithm. We unwrap that, okay, the reward function can change and that causes non-stationary issues. And then even deeper than that, the deep learning model is being trained with Atom, which has its own memory. So basically, where do these models at somewhere in the training process effectively store in themselves a type of memory? So then if anything changes, that memory actually becomes a problem because it's memorizing what was happening from before. So there's many layers where these can be introduced. Okay, any other questions? All right, good for now. Okay. Oops. All right. So there was a few papers in trying to basically understand, okay, what is related to this like plasticity loss? And plasticity loss in this case is now like things that the neural network is essentially memorizing in its weights and such that it's not good at changing its distribution, because this is often related or has been related to like looking at the weight norm for all of the weights in the network, because this could be related to like having large outputs if you have really large activations in your network. Okay, doesn't seem to be strongly correlated with that. Then people would look at, okay, what about the weight rank? So this is, you can look at the rank for the actual matrix. You know, if things actually start to become poor rank, then they can't represent certain values properly. And that would mean things are maybe not very plastic because it's basically lost its ability to be able to represent certain functions. It's a bit correlated, but not strongly. And then there's basically a couple of other examples for this, like looking at dead units in the network. They're basically, if you've got like a ReLU in your network, it's basically outputting here. So it's like 0 all the time. So it's kind of like calling it dead. So they're essentially not going to learn or change anything about the output. This also does not seem to be highly like correlated with some type of plasticity loss. Maybe the NLP is a bit better. But long story short, there's a lot of these kind of looking at the challenges and like what's going on in the network, trying to understand what's causing this plasticity loss. If we look at it from like a matrix factorization point, it doesn't really seem to correlate a lot with plasticity loss. So there's actually still kind of like an open problem here of figuring out, is there a way to determine while the network is training that it's losing plasticity? Because at least in that case, we can figure out how to do resets or something because we know it's starting to overfit. Because when we know if it's overfit, we can like act to make interventions. But we're still pretty poor at being able to understand, in particular, when the model is overfitting, when it's, you know, basically losing its ability to have forward transfer. That's unfortunate. I would like to have better news for you here, but the good part is it means like you can go study this and this will be really helpful. This is basically what is keeping the deep RL kind of community from being able to use RL in like really huge and diverse tasks, because it's has these plasticity issues in the network as it's training. But that's also why things like continual Bragg prop are maybe interesting, because the whole idea there is totally just about trying to get around plasticity issues. That algorithm probably still needs some more time and development to scale, and I'm sure ideas across those two methods will be kind of integrated. Okay, the interesting part after a lot of this analysis in this paper is that it seems like layer norm is a really good thing to basically be able to use to adjust here. I know, I'll do this for a second. I know we talked about that a bit in like the last lecture as well, where layer norm also seemed to be pretty good for DQN and being able to scale that up. But it seems like it's because of the way layer norm works, it's kind of like controlling the distribution of outputs for the network and at each layer. So it's kind of in a way making sure that there's always a good loss landscape between each layer, such that there's not like a whole bunch of dead units or something where basically there's no outputs or no distribution can be changed anymore. So maybe it's at least a little bit better at recovering the ability to be able to still have some more forward transfer. Even if it takes a bit longer, at least it still exists. So some of these kind of like activation layers end up seemingly to be pretty key. And I'll like in the next couple of papers, there'll be kind of, you know, noting different things. And each one is also going to say like layer norm is extremely important. So if you're thinking about scaling your network, have a look at layer norm. Short answer. Okay, let's great. Go on to the next one. Okay. Well, actually, for a second. Any other questions about this like plasticity stuff at the moment? Okay. Good, because now we're going to get into a slightly more, maybe a different way to tackle this is actually to use representation learning and different kind of auxiliary objectives. Because often for a short version of this, so like even if we had a policy where we wanted to have a really high replay ratio, part of the problem is it becomes very biased and overfits that data. But what if there was a representation that we could enforce into the policy structure such that it can't really overfit that data as much? Because at the moment, it's just sort of like model free, train all this data. Hopefully the model won't overfit, but that doesn't really seem to be the case. So in this process, and this also requires even a lot of data to start to overfit that. So maybe there's a way we can start to change the learning process in order to be able to have this be like have a nicer structure. And we can kind of like finally talk about some of these concepts now that we've covered model-based RL and model-free RL enough and understand what's going on. So one of these is a paper that's doing temporal difference learning for model predictive control. And the idea is really to combine some of the concepts for model predictive control and temporal difference learning. Here, where the idea is to basically use a latent representation for the Q function, such that kind of like train this latent representation. The idea is it should learn something about the dynamics and then have it in the future after a couple of steps predict what the Q function should be. Maybe I'll skip forward to this diagram. It's basically a bit more like this, although this is for the second version of the paper. There's some encoder. There's going to be some latent representation that's basically trying to figure out, you know, in a lower dimensional state, what is going on, because the highest dimensional state isn't always that informative or well structured. And then this particular model is trained to predict the Q value, the reward, and the action. It's not being trained to like predict the actual observation. And we've talked a little bit about having to predict images is sometimes a bit overkill, because it might, in this case, like learn to predict the tiling in the background of this dog video, which isn't really as important for the task, and spent a lot of its capacity on that. Okay, so hopefully this model makes a bit more sense. And then the idea is now to just use this latent representation where it can do some rollouts and then figure out how to take that action in the future, and then basically kind of bake that into the Q function structure. So now it's using a lot more data to learn just this forward model. And a forward model can usually be like a bit more sample efficient in the way it can be trained. And then this results in some pretty good performance improvements where this is compared to just normal SAC. And then this TD version given what looks like 5 million steps in the environment. So the structure can end up working out pretty well. It doesn't require any more data, so you don't need any special pre-training, no additional data about the environment, just predict the reward, the action, and the Q function, and do it in this embedded structure for having this MPC model. And this is nice because it gives the model basically, it's kind of like taking advantage of the data more, giving it a bit more signal here because it's going to learn something based on MPC. And yeah, does that make sense? So any questions about this? Just makes total obvious sense. You basically already thought of this, and this is just something that just like obviously connects together. Conceptually, maybe. Okay. Good. I mean, there's still a bit of, like devil's in the details. As much as you come up with a good idea for being able to do deep RL, that is usually 10% of the time, the 90% of the time is figuring out, like what should H be? How big should the latent vector be for this to actually work? How far into the future it should predict? But these all help condition this a little bit better. Okay. And then there was basically a second version of this paper called TD-MPC2. So these are both really nice papers. So if you need a pretty good sample efficient algorithm, this would be a good place to start. More so what was done in this paper is still thinking more about, remember, the point is that the latent representation should encode useful stuff for the task, and like only that if it can, rather than any things that's non-useful. So the way you know to encode something that's most useful for the task is have it learn to predict the reward. It's the thing that is the task. So learning from predicting this, much like how we talked about GCG from a while ago, which was a model that would predict reward for like the next 10 steps and then a Q value. So it would learn a lot from those rewards. But basically this TD-MPC version is now, okay, look, this TD-MPC model can also be used across tasks. So if you've got a bunch of different tasks, it's still possible to learn a bit of a shared representation across these different tasks, and that can also really help learning. It turns out it's also pretty helpful for being able to scale model parameters as well and still be able to get performance. So this structure, if we all remember too, like a forward model is supposed to be like task independent. It just takes in a state and an action outputs a state and a reward. So it can technically be trained over all the data you got. So then you've got even more data you can train this model for. And this can result in some pretty good performance, even over itself, even over Dreamer, which is another model-based algorithm that we've discussed, even over versions of SAC. So it's always good to be able to take advantage of some extra data or some extra task training. Okay, any questions? Okay. This one also seemed completely obvious because of how well structured the class is and how well we follow the storyline into the next paper. Probably not. I don't think I quite get enough sleep to be that perfectly accurate. But also feel free to like ask questions on the Discord channel if you've got something that comes up later. Maybe you feel like reading these papers this evening or on the weekend rather than skiing, something like that. Everyone has their own preferences. Okay, so I just wanted to get to one or two other ones, which are also really related. So this last, I'm not sure, I don't think this is quite the last one, but this is a different one. So now this one is even more about scaling and also not having to even provide as much structure. So like not even the MPC level of structure. This one's pretty new, but it was published at NeurIPS last year. And in this case, it's called Bro for these reasons. And you can see like gray here is now TD MPC2, where it performs maybe similar in MetaWorld, but does a lot better in some of these other environments. There also seems to be this really weird fixation in the community on this dog task. Somehow it's really hard, people have sort of said. And they're like, if you do well on that task, cool, that's a whole paper. It actually doesn't look like really hard of a task, but we can maybe talk about how it's actually really simple to walk if you've got 4 legs, but we can get into the details on that later. But a lot of this is being able to, so this has got the replay ratio again, and being able to get a model. This is the purple that's up here, or purplish pink, that scales well, even if there are lots and lots of parameters for the network. Because the idea is now this network can, ingest a lot of the data that's been collecting and not overfit that data such that it can still like learn from the new data that's collecting. And for some of the details there. Okay, so then how is this actually achieved? Not just doing it by just using those specifically. So again, layer norm seems to be really key in order to not end up overfitting the data early on. That part we've already talked about. So this one is going to be, some type of residual network design. So it's kind of like using a ResNet again. But one of the ways they were actually able to structure their network, even in the case where images are not being used, is to kind of construct the network such that parameters can be added. Like there's kind of like a ResNet block in this network, and then the network can add like n blocks into this that kind of feed into itself, so it can make itself longer or deeper in order to learn from. And that's what basically constructs more of these number of policy parameters. Okay, but one of the really interesting things that I want to make sure we talk a bit about, okay, scaling the critic seems to be more important. Scaling the policy really didn't help improve this model much. Any idea why that makes sense? Some thoughts. It's kind of like it's a bit of a weird finding, but maybe if we think about it a little bit too long, we'll start to get some ideas. Mm-hmm. Yeah, there's basically like a version of this. The short answer is yeah, it's kind of harder to train a Q function than a policy. It's like one way to say that. Because the Q function now has to learn the best action at every single state across all possible states. It has to encode quite a bit. The policy then just needs to figure, okay, what's the best trajectory? It's literally like, thank you, Q function, for my best trajectory. You can go away now. And it's only really got to learn how to replicate that. It's really just got to learn how to do like kind of really good optimal behavior cloning. So in that way, it's almost like, okay, maybe the policy isn't the thing that needs so much capacity. It's just the thing that sort of like gets the last bit of information jammed into it such that it's learned the optimal like idea out of that. And we'll see if we get some into the details for stuff in the class too, because there's actually a growing kind of group of literature. And I think we'll actually have basically this discussion on Wednesday. So like next Wednesday will be an in-class discussion here. We're really just going to talk about the pros and cons of basically doing QLearning versus doing behavior cloning, because it's kind of highly related to this. because learning a Q function can be hard. There are some advantages, though, that are important for being able to learn a Q function. Maybe it transfers a little bit better if you don't know what your next task is going to be, rather than just doing like a policy or behavior cloning. But this is something to really keep in mind. It's also one of the weird reasons when I look at people, whatever, um, people are doing research across different problems. And I don't know if everyone remembers the ridiculousness that happens on social media, but some people thought like OpenAI had found Q star, which is like the best Q function possible. And then maybe RL people can kind of scoff at this. Like they haven't even learned how to generate an optimal policy, and they're claiming to be able to do this thing that's seemingly much harder, which is to understand how to generate any optimal plan at any point in the entire state space of the whole universe. So it's sort of like if we can't currently ask some of our larger models just to do this plan for us right now, then I doubt it's actually going to be able to model a Q function either, which is more complex than just coming up with a single plan. And that this will still be a challenge for a while. And that's maybe also reflected in because we had that lecture on like using language models for reward functions. And they're still not like strong at being able to model reward functions very well either. And that would be one step before being able to get a good Q function. So something about this, I don't know, is going to keep people up late at night for a while as they think about it more and work on it more. Okay, any other questions about that? Good for now? Okay. There's still definitely a lot of challenges in these models. One of them, okay, so we talked about off-policy learning. It's really hard to include memory. Okay, so before this would normally be something like an LSTM or something like that that would keep around memory so you could model a POM-DP really well. The basic design for these algorithms are terrible if we ever wanted to include something like that inside of the network. Partly because, you know, the current, like if you were to run a trajectory, that would mean that the network, if you had an LSTM, needs to store that history so far. So you can't really just pull batch updates out of the replay buffer because it kind of needs to know where it got to in that state. There's certainly a couple of algorithms that would store the state of the LSTM inside of the replay buffer as well as like an option, but that was pretty unstable. These still need a lot of on-policy data. So even though the replay ratio is being increased, if the replay ratio or basically the policy gets too out of sync with the Q function that's modeling it, diverges pretty quickly. So that's still part of a challenge. Apparently layer norm is a good option to try and avoid some of this. Talked about it a bit, like a fair bit already in this, like QLearning takes some time to stabilize. There's lots of different learning issues, partly because there are more networks that'll have to be learned at the same time. It takes a fair bit of time to start working. So often in the learning curve, it's going to be flat for a while, and then it'll finally start to pick up. And it usually requires more hyperparameter tuning, which is unfortunate, but that's kind of the trade-off we're making. With the idea is to have an algorithm that's more off policy, it's more sample efficient. It's going to come at some costs. It comes at costs in having more models, more hyperparameters, more things to learn to adjust. With all those hyperparameters in mind, do at least like store it in your memory bank, but often slower is faster. So like anneal things slower, reduce exploration noise so that the policy distribution isn't changing so much. All these things actually keep stability, and then often the algorithm actually learns faster. And then this is usually like annealing rates, reduce exploration noise gradually over time. Maybe use something like the Huber loss to control how large the error can grow when doing your Bellman updates. And a bunch of other options here for all of these. Like sometimes QLearning helps. N-step returns, almost always necessary to reduce bias. And then, like I was saying, even related to this, you can also, I guess, do the same thing. Schedule your exploration and learning rate, high to low. But yeah, be careful about using Atom. It does normally work, But if your problem is highly non-stationary, you might actually try SGD instead of Atom. Basically, if the statistics of your learning process are changing all the time, Atom's not going to help because you're sort of just like fighting against what it's doing. Okay. Any questions about these so far? No, good. Okay. These are like tips because at least someone hasn't made a nice blog post page of like the 33 things to check when you're coding PPO. So these are like the 10 things to be careful about for any general off-policy algorithm. And there's even more in other papers. Okay. I'll stop there for now. Hope you're good. And then I'll see everybody on Friday in the Agora, the big room, and we'll chat. And then we'll get into offline RL, where we basically, our replay ratio is now infinity. Is one way to think about it. All right. Take care, everybody.